The height above the ground of an angry bird that has been catapulted into the air can be modelled by the quadratic function h of t u is equal to ut minus 4.9 t squared plus c, where t is the time in seconds and u is the initial velocity of the bird and c is the initial height of the bird. So this is the initial velocity and this is the initial height of the bird. Now the 4.9 comes from half times gravity, if you want to relate it to your physics. Red, which is the name of an angry bird, is catapulted from a platform which is 30 meters above the ground at an initial speed of 20 meters per second. What will be his height after 3 seconds of flight? What will be the maximum height above the ground? When Red hits the ground, for how long will he have been in the air? So let's just have a quick look at this with a GeoGebra applet. So the initial velocity is 30. Sorry, 20. And the initial height is 30, so we've got a height there of 30. So these are the things that we're going to actually now calculate. We're going to actually calculate the maximum height, where he is after 3 seconds, okay, and then the time of flight is this time here, okay. So this is a sort of a graph of a quadratic, and it's a practical problem involving a quadratic. So h of t is going to be equal to ut minus 4.9 t squared plus c. So u is 20 meters per second, and c is 30 meters. So h of t is going to be 20t minus 4.9 t squared plus 30, because the initial velocity was 20 in the question and the initial height is 30. So we want the height after 3 seconds, so we need to calculate when t is 3 seconds. So h of 3 will be, we just substitute 3 into this, 20 times 3 minus 4.9 times 3 squared plus 30. That's going to give you, if you work it out on your calculator, 45.9 meters. So h of t is equal to, if we rewrite this in the general form of a quadratic, we write the t squared term first, so it's minus 4.9t, because it's minus 4.9t, plus 20t plus 30. So we relate that to the general quadratic, at squared plus bt plus c. Normally we have x instead of t, but we're talking about time here. The greatest height will occur when the time is equal to minus b over 2a, which is the vertex of the quadratic. And remember, this is the formula for finding the x-coordinate of the vertex, but this time it's a t-coordinate because we're looking at time. So, from that, a is equal to minus 4.9, and b is equal to 20. So substitute that into that formula, we're going to get that t is minus 20 divided by 2 times minus 4.9. That gives me 2.0408 seconds. And we don't round off, because of course what we're going to do, we're going to now put that into this instead of t to get the actual maximum height. So the greatest height occurs when t is equal to that value. So h of 2.04, okay, don't round it off. Okay, so it's 20 times 2.04 minus 4.9 times 2.04 squared plus 30. So I work that out on my calculator, get 50.40816 meters, which is 50.4 meters to 3 significant figures. If we go back and have a quick look at this, we can see that we've got the same answer here. Okay, this is the maximum height. Right, now what we're going to do is we're going to have to calculate this time here, where it actually hits the ground again for part B. So when Red hits the ground, sorry, it should be a ground again, h of t is equal to 0. So we're going to need to solve for 20t minus 4.9t squared plus 30 is equal to 0. This is a little bit beyond the course, so we use a little bit of technology to help us do that. So jumping to our GDC, So we're on our GDC, so we need to go to a graphing mode. So hit a graphing page, open a new graphing page, and then enter the function. You have to enter it in terms of x. So 20x minus 4.9 x squared plus 30. Enter. Now we need a suitable view window because we're really interested in this bit from here to here. So what I'm going to do is go to Menu, Window Zoom. So you need to know your zoom technique. So it's always better to put -1. You get a bit of the y-axis that way. And I'm going to set this to 6. I'm not going to worry about the y for the moment. Press OK. And then what I'm going to do is Menu, Window Zoom, and then do a zoom fit. Okay, so what that does, once you set the x-axis from -1 to 6, it will automatically set the y-axis. Okay, so we were interested in this point here to answer the part B. So Menu, analyze the graph number 6, and that's a 0. So we'll go press the 0 slightly to the left of it, and then to the right, and we get the time of flight will be 5.248 seconds. Now while we're at this, we can actually now look at some of the things from part A. So analyze the graph, we can go for the maximum point. Okay, so the maximum point occurred at 2.04 seconds, and then at the maximum height was 50.4. The initial height is this point here. We can find that by doing Menu, Trace, Graph Trace, and then entering 0, enter, escape. Okay, and that gives you the starting point. Okay, we're only interested in finding this point for the question, but this is going back to the initial part of the question. So there's a screenshot of what I've just done. You should draw a little sketch now. So a T, and put it back in terms of T and H of T. I've highlighted this point here because that's the one we're interested in. Drawing the curve, labeling it H of T is 20t minus 4.9t squared plus 30. Marking on that point 30, this point here is 5.248 seconds. This is the greatest height, which is 50.4 meters at 2.041 seconds. And this is the time of the flight, because this is when it was in the air. And so red was in the air for t is equal to 5.25 seconds. Okay, so this has been a video to show you how to model a computer game using quadratics. I hope you understand, and thank you very much, and I will attach the GeoGebra app in the notes of this video. Thank you very much for watching.